in the last class, we looked at the Gauss's law, and we did some examples on the Gauss's law. We looked at the Gauss's law in the integral as well as differential form. And then we did it for a point charge. And then we did it for an infinite line charge. And also we did it on the sphere, a volumetric sphere, which is carrying a uniform charge density. So these are the examples that we did by applying the Gauss's law. And we have seen the steps whenever you want to apply Gauss's law for any, say source, any charged source, then you have to enclose it in a hypothetical Gauss's surface and then apply Gauss law on that surface. And based on that, you will get the answer. And as I told you, this becomes very handy when you have some symmetry in your problems. If you don't have the symmetry in the problems, then it will not become handy. It will not become easy. So Gauss's law and Coulomb's law will become the same, because as I told you, you will not be able to do this part. You will not be able to take D outside, and you will not be able to replace this with 2 pi rho h. So these things, if you cannot do it, then it is more or less the same as the Coulomb's law. So this was our last class review. So now today we will go to lecture 4, where I'm going to introduce you with what is called as the electric potential and potential difference. So this, you are very well aware of it. And now we are now trying to derive its expression from the electromagnetics point of view. And remember one thing, electromagnetic theory is a more comprehensive theory compared to what you have seen in your, say, electrical circuits or electronics, where you put the voltage and the current. But if you want to go and look at the microscopic level, okay, so then electromagnetic theory is the main theory which explains all these things. So it depends on, what you want to analyze. So there are some theories that, your circuit theory will be difficult to explain. Then you need to go to the electromagnetic theory. But some of the, topics in electromagnetic theory will also be difficult for you to understand. Then you go even further in detail. That is called as the quantum theory. So all these are the different theories which allows you to understand. And as an engineers, what we do is we try to find, the theory which is easier and relevant to us and which can explain us what we require. So that's why we work with circuit theory in 2 level. Now in 3 level, we are going into a little bit detail, which is electromagnetic theory, because as an engineer, we should know all these things. Now the quantum theory, this is more specialized. So if anyone wants to get into, say, quantum optics or quantum mechanics and other things, then he can go and look into that theory. So let's come back. So now what is the potential difference? So potential difference, again, I am now bringing the definition from what you have studied in physics. So it's the work done per unit charge required to move a test charge from an initial point A to a final point B. So this is the definition of potential difference. So it is saying that you just need to do some work, and that work, you are normalizing that work with respect to the charge. And this, what is this work? It is done by moving a test charge from an initial point A to a final point B. So the potential difference VAB is nothing but work done per unit charge. Work done per unit charge. Now what is this work done? Work done, I am borrowing the expression from your physics. It is nothing but F bar mechanical dot dl, and I'm moving from A to B. So let me just freeze this. Okay. So here, so there is some charge here. Okay, you can think that there is some charge here, and this charge is Q. Okay, and now we know that because of this charge, there is already a force exerted, right? Along it like this. These are nothing but our force. Now, what you are doing is you are now moving a test charge from this point A to this point B. So when you want to move this test charge from point A to point B, then you have to do some work, and that work is from A to B, F bar dot dl. Now, what is this force? What is this force? So when you want to move from point A to point B, the force will be almost equal to opposite of the force created around here. It is almost equal to the force which is created by this charge Q, which is already placed here. So this charge Q has created a disturbance here. And now when you want to move a test charge within this disturbance from A to B, then the force will be almost equal to the opposite of that disturbance to move. So if it is positive, so force will be, pushing on this side. And then if you want to move this charge, then you have to apply the force on this side, and slowly you have to move along this path A to B. So that's why I'm now replacing this mechanical force by the negative of my force, which is nothing but the disturbance created by the presence of this charge Q. So it is minus F bar dot dl. And now we know the relationship between this disturbance, which is the force, and the field which is created here. And we know E is equal to F bar over Q. So F bar is equal to E bar times Q. And minus F is equal to minus E bar times Q. So this minus F, I'm replacing it with minus Q times E bar dot dl. Got it? And this is because of the presence of this charge capital Q, which is making this disturbance, which is our force disturbance, and also the electric field. Now, if you just simplify this, so if I may just remove this. So if I simplify this, what I am getting, Q and Q will cancel out, and then I will get the potential difference VAB is nothing but minus integral A to B E bar dot dl bar. And the units are in volts. So this is telling us that the potential difference from A to B is, what you do is just you look at what is the electric field in the surrounding. And whoever has generated that electric field, we don't need to worry. Maybe this electric field here in the surrounding, this electric field in this surrounding, maybe it is generated by some charge which is here. We don't care about the source. We just care about the electric field. So this is the electric field of the surrounding. Now, what is the potential difference definition? It is saying that what you do here, the amount of work that you do in moving this test charge from here at each point. And at each point, you are doing E bar dot dl bar. So what you are doing, you are taking this electric field and looking at its component. Okay, so I can give you an example. So if this is my electric field, I'm just taking its component along this direction, which is my dl. That's why it is E bar dot dl. And this electric field, you have to go against it because the electric field is in this direction. So you have to go against it. That's why you have this negative. So this is called as the definition of the potential difference in terms of the electric field. In terms of the electric field. So this is the potential difference when you are between point A and point B. Now, what is absolute potential, or sometimes it is also called as simply potential, is if your initial point is placed at infinity. Sometimes it becomes easier for us in our analysis to place a point at very, very far away point and assume that here, you know, the potential is 0. So it's a very far away point. So now it is the voltage is nothing but it is your initial point when you slowly move your initial point from B, and when you go and put it at infinity, very, very far at infinity, then you get what is called as the absolute potential. So the absolute potential that you see at this point P is equal to minus integral, instead of point A, which is my initial point, I'm writing it as infinity, to my point B, which is my point P here, E bar dot dl. This is called as absolute potential. And this expression satisfies when the potential at this point at infinity is 0. This is our assumption. So this is absolute potential. This is the potential difference. Now we know the relationship between these two guys very well. You have done it in circuit theory. What is the relationship between these two? Now let's cross-check that from our electromagnetic equations. So now if I have a potential expression at point A, VA is minus integral infinity to A E bar dot dl bar, and the potential at point B is equal to minus integral infinity to B E bar dot dl bar. So these are my two potentials at point A and at point B somewhere in free space. Now, what will be the subtraction of this? VB minus VA. So if I subtract this VB minus VA, this will be equal to your VB as it is minus integral infinity to B E bar dot B dl bar minus A. So minus of minus will become plus integral infinity to A E bar dot dl bar. Now for the first term of your right hand side, I am now swapping its limits. So when I swap its limit according to our integral, our mathematics, our integrations. So if you swap the limits, then the sign will change. So your plus will now become minus. And now it is integral A to infinity E bar dot dl bar minus integral infinity to B E bar dot dl. And now if we apply the again in relations from integrations, A to infinity, infinity to B, this can be written as A to B. So it is minus integral A to B E bar dot dl. And what is this minus integral A to B E bar dot dl bar? It is the potential difference between point A and point B. So the potential difference between point A and point B is nothing but potential at point B minus potential at point A, or the absolute potential at point B minus the absolute potential at point A. And this is what we have used in our circuit theory. VAB is equal to VB minus VA. So this is what it is saying. The potential difference between points A and B is equal to the absolute potential between them, and also it is VB minus VA. Now, let's take an example. So in our case, we want to find the potential due to a point charge located at origin. So here what we are saying, so we are saying that we have a charge. See, this is the charge, and this is the charge Q, and this charge Q is placed at origin, and therefore because of this charge you will have electric field, right? So you will have electric field everywhere, here, 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 even here, electric field. Now what we need to do is we need to find the potential which is created at the which is created by this electric field, by this point charge Q, which is placed at origin. So this point charge Q is placed at origin, and we need to find the potential created by this charge. Now to find the potential created by this charge, let us first make some say our problem statement. So what I'm saying is, let me assume that this is my point P. This is my point P, where I'm going to find the potential difference. Okay, where I'm going to find the potential, not potential difference. And this point P, I need, because since I need to use in mathematics, I need to define this point. So I'm saying that this point P is at a distance of A from origin. Okay. And then there is another initial point which is at infinity. So this point is at infinity. Okay, or very, very far. Just think like very, very far. Because thinking at infinity will be difficult, because in that case you cannot define its distance from origin. So let's assume this to be very, very far. So this is very far, very far. And the distance between this with my point which is placed at origin is this R. Now let's find the potential at this point P. So the potential at this point P, Vp subscript P, or now I'm just say dropping the subscript. I'm just saying the potential V is equal to minus integral infinity to this point P E bar dot dl bar, which is equal to minus infinity. Now what is my E bar? I'm now substituting E bar. Yes, we know the electric field which is created by a point charge which is placed at origin. What is the electric field created by a point charge placed at origin? Is Q over 4 pi epsilon R square AR. So I'm substituting the electric field created by the point charge here. And dot dl. So now dl is this direction, right? And this direction is nothing but in your spherical coordinates, because now I need to do the integration. So now I need to evaluate this integral in a coordinate system. And the best coordinate system for a point charge, because the point charge has radial electric field, is spherical coordinates. So if we look for spherical coordinates, then this distance moving the charge from here to here, this distance will be your radial distance. So that's why dl bar is replaced by AR dr, is replaced by AR dr, because it's the radial distance. This is your dr and AR is the unit vector. And by the way, guys, I'm not putting minus AR dr here. We are moving in the opposite direction. We are moving in the opposite direction, but I'm not putting minus AR. Why? Because in the definition of the potential, this minus, this movement in the opposite direction is already taken care here. See, it is already taken care here. That's why. Now, infinity to P. So now if you see here, your integration is with respect to dr. So therefore, now the limits of my integration is this infinity will be my r. So r will take the infinite value and the point P. What is my point P? This is my point P. And at this point P, what is my r value? Is A. So therefore, r is equal to A. Therefore, now AR dot AR will become 1. So therefore, the dot product will be gone. So it will be Q dr over 4 pi epsilon r square. Integral r is infinity to r is equal to A. And integral of 1 over r square is what? Minus 1 over r, or r to the power of minus 1 over 1. It's the same. And this is the units. This is the limits, infinity and A. And if you substitute here, you will get that the potential is just Q over 4 pi epsilon A. Q over 4 pi epsilon A. This is the expression for the potential. Potential due to a point charge placed at origin. And what is this A? If you see here, A is nothing but it is the distance of my observation point from the origin. A is the distance of my observation point from the origin. So if I make my observation point here, then A should be replaced by this distance. And now let me generalize this. So if I generalize this, I don't want to use A, B, C because this is the radial distance. So this radial distance, I can replace it with R. So this is the general expression. It is Q over 4 pi epsilon R. So this is the potential which is created by a point charge, and the point charge has a charge of capital Q, and that point charge is placed at origin. So this point charge, what we have studied, will do two things because it's a source. First, it will create a disturbance, which we are capturing under what we say it as electrostatic field or electric flux density. But at the same time, it is also creating a potential, and that potential is Q over 4 pi epsilon A. And as we have seen, the potential will always be a scalar. It will not be a vector. See here, the potential, it's a dot product. It's a dot product. So therefore, your potential will be a scalar. So this will be the potential. And this is the example we have derived for placing my point charge at origin. What about if my point charge is not at origin? No issues. If my charge is not at origin, see, if my point charge is somewhere here and the origin is somewhere here, you can use your position vectors as we did it in the Coulomb's law. So if r dash is my position vector of my point Q and P is my observation point and its position vector from origin is r bar, then we need to find this, and this should be replaced here because this is the distance between your charge and the observation point. So now it is replaced by the magnitude of this distance vector, and the magnitude of this distance vector in terms of position vectors is r bar minus r bar dash. So this is my distance vector r, and if I take a magnitude of that, that will be the magnitude of my distance vector. So this will be for the point charge which is not placed at origin. Okay, so this is about the potential. So now let's take an example. So now example is saying that I have a point charge of 5 nanocoulomb, which I have placed at this particular point of 1, 1, 0 in free space. So it's a free space, epsilon 0, free space. Now, first we need to find what is the resulting potential at point 2, 1, 0. Now, what is the resulting potential at the point 2, 3, -2? And also we need to find the resulting potential difference. Okay, so here again, so here your point Q is not placed at origin. So therefore you need to find the distance vector. And since here your potentials are scalar, so rather than, you know, finding the distance vector and then finding its magnitude, you can directly try to see if you can find the magnitude of this distance vector. So for VA, it is equal to Q, this is Q, 5 times 10 power minus 9, 4 pi epsilon R. So this is the distance vector. So what is the distance here? See this one? What is the distance vector here?
It is 1.
Yeah, so your distance vector will be, you know, it will be AX plus 0 plus 0, right? So that's why it is root of 1 square, which is 45. So if you simplify this, it is 45. Now what is VB? So first find the distance vector and then find its magnitude. So distance vector will be 1 square, 3 minus 1, 2 squared, minus 2 minus 0, minus 2 squared. So this should be minus 2. So not to worry. This is minus 2 square. So therefore it will become positive. And therefore it is 15. And last, the potential difference is nothing but VB minus VA, which is 15 minus 45, which is minus 30 volts. So this is the potential created by a point charge. So a point charge has created this potential everywhere in your space. Now we are finding this potential at a particular point, and that particular point is this, and this particular point is this. And if you want to move any test charge from that point A to point B, then the potential difference will be minus 30 volts. Okay. Now, as we have done for our electric field satisfies the superposition theorem. In a similar manner, your potentials will also satisfy the superposition theorem. So if in a space you have several point charges and you also have some charge distributions, then what will be the potential, the overall potential at an observation point P? So you have so many charges, Q1, Q2, Qk, Qn, and these are their distance vectors because these are not placed at origin, and this point P is also not an origin. That's why these are your distance vectors. And then you have a line charge, you have a surface charge, you have a volume charge. Then what will be the overall potential at this point P? So the overall potential at this point P will again be simply the superposition of individual sources by, you know, applying the superposition theorem. So therefore, the potential for all these point charges, I can put it in the summation form where K is 1 to N, Qk over 4 pi epsilon Rk. Rk is the distance vector. And remember guys, distance vector always points away from the source. So it will always point from the source towards the observation point. Very, very consistent with what we have done in the Coulomb's law. So the distance vector always points away from the source, that is from the source towards the observation point. Now, this is for the point charges. For the line charge, again, how we have done it for the electric field, same thing is for the potential. So we know the expression, we got the expression of a point charge. Q over 4 pi epsilon r is the potential due to the point charge. Now for charge distributions, this will change. Q will change, very similar to what we did it in the Coulomb's law. So for the line charge, if this is my elemental small length dl, so if this is the charge carried by this elemental length dq, which is rho l dl, and its distance from the point P, the distance vector, see the arrow, distance vector is r bar, then the potential is given by integral over the length L, rho L dl. So this is a sort of giving me the charge over 4 pi epsilon r. And for surface, it will be rho s ds. And for my volume, it is rho v dv. And remember here, I'm putting r, but these r are not same. That's why I'm putting here. For this case, r bar is nothing but from your elemental length to your point P. And here r is from your elemental surface area to your point P. And here your elemental volume to your point P. This is the elemental volume to your point P. Elemental surface area to your point P. This is how you can find the potential due to various charges or charge distribution at an observation point P. So let's take an example. This is a very nice example. Now, what is this example? The example is saying that you need to find the potential at point A. So this is my potential at point A. Okay, so let me just make it a little bit small. Oh, yeah. So potential at point A. So this is my point A. So we need to find potential at point A, my observation point, due to the charges shown below. So these are given to us. So what are the charges that we have? So we have a point charge, which is -2 distance. It's placed at -2, 3. So it is placed at -2, 3, and z is 0. Now you have another point charge, Q1. This is Q2, which is placed at 2, 0, 0. Okay. And then you have a line charge. So if you see here, this is your line charge. And it's a finite length line charge. And its length is given to us. So this is -1, this is 1, and this is 3. So how are you going to find the potential of all these three at this observation point P? So first, let's find the potential due to the point charges, which is very straightforward. So for this Q1, -3 nanocoulomb, what it is? Q1 over 4 pi epsilon R1, right? So it is, okay. So it is Q1 -3 nanocoulomb divided by 4 pi epsilon 0. Why? Because it is in free space. So epsilon 0 in free space is 10 power -9 over 36 pi. And R1 is 2. R1 is 2. This is your R1. Okay, this is your R1. R1 vector. Come on. Just a second, guys. Okay, so this is your R1 and it is given by, and it is given by 2, right? Because this distance is 2. Now, the next one, V2. So V2, this will be your R2, right? So this will be my R2 bar. So how can you find R2 bar? You know it very well. To first find, this point is -2, 3, 0, and this is your origin. So therefore, your the magnitude of this will be, so your Q2, 5 nanocoulomb divided by 4 pi epsilon. Now, what will be this distance? It will be root of 2 square plus 3 square, correct? So this will be your distance, root of 2 square plus 3 square. So which is 45 over root of 13, so 12.48 volts. Now the last one. So the last one, again, in this last one, with this example, you are again learning something that we did it in our Coulomb's law. Remember, in the Coulomb's law, for the finite length, you can apply the general expression. So here also, to find the potential of a line, so let's apply the general expression. So for that, let me first define a small elemental length. So this is my small elemental length. This is my elemental length dl dash. But in this coordinate system, this is along the x direction, right? So can I say it same as dx dash? Okay. And now we need to define its location. So first I'm saying that this is located at a distance of x dash, and this is my distance vector r. And my distance vector r will no longer be a constant, because as my dl will be moving from here to here, your r bar will also be moving from here to here. So therefore, it will not be a constant. It will be a function of the spatial coordinates. So now how to get this? So VL is integral over L, rho L dl over 4 pi epsilon r. So rho L is what? 2 nanocoulomb per meter. So it is 2 nanocoulomb per meter. dl is nothing but my dx dash over 4 pi epsilon naught r. Now what will be my r? So I need to go from here to here, right? Again, it is similar to what we did it in our Coulomb's law. I want to go from here to here. So can I first go from here to this side? And what will be this vector? Minus x dash ax, right? Because I'm going in the opposite direction, and this distance is x dash. So it is minus x dash ax, and then I will go down. And now what is this length? This length is 3. But I'm again going in the opposite direction of my ay, because my y is upwards. So my unit vector ay is upwards, but I'm going in the opposite direction. That's why it is minus 3a. So once we get r dash, the r vector, now what will be the magnitude of this r? It will be root of, so it is minus x dash square, which I can just say x dash square, minus 3 square, which I can say it as 3 square or 9. And this is here. Okay. Now, what will be the units of my x dash? What will be my units of this x dash? So dl will be moving from here to here to cover the length, right? So my x dash will take units from -1 to 1. -1 to 1. And then you can continue and solve this, get your answer. And once you get your answer, the overall potential will be V1 plus V2 plus this answer. Clear? So this is how you can find the potential for a finite line, again using the general expression of the potential. Okay? So now there is a couple of properties of our potential difference, and the properties is, first is the potential difference VAB, which is integral minus a to b e bar dot dl. Sorry, it should be dot dl. Dot should be here. So it should be dot here. E bar dot dl is independent of the path. That means if you want to go from this point A to point B, you can take this path 1, you can take this path 2, or you can take this path 3. Any path you can take, you will get the same answer. So that's why we say this VAB1, VAB2, VAB3, they are all independent of path. So all are independent of path. And that is why if they are independent of path, then again from our vectors, vector fields, you will see the following. That is coming later. So if it is independent of the path, VAB1 is equal to VAB2 is equal to VAB3, then we are deriving something. So what I'm deriving? I'm equating these two. VAB1 is equal to VAB2. So VAB1 is what? Minus integral a to b e bar dot dl bar. So this is path 1. This is path 1 is equal to minus integral a to b e bar dot dl bar. This is path 2. Okay. Now I'm taking the left hand side to the right hand side. So this minus becomes positive. So integral a to b e bar dot dl bar of path 1 minus integral a to b e bar dot dl bar of path 2 is equal to 0. Now this one, I'm just rearranging that. What I am doing, I am now changing the limits of this second term of my left hand side. So instead of a to b, I'm making b to a. So if I make b to a, then the sign will change, right? So the sign will change, and then integral b to a e bar dot dl bar is equal to 0. So now what does this say? It says that I'm integrating e bar dot dl bar from point A to point B. And then I'm integrating again from point B to point A, e bar dot dl. And it is becoming 0. So I'm going from A to B, and then I'm coming down back from B to A. That is nothing but closed line integration. So the closed line integration of e bar dot dl is equal to 0. So if you go from point A to point B, and then if you return back from point B to point A using any other path, so this is what? This is closed line integration. So because you're starting at the same point and you're returning to the same point, same starting point. That's why it is, I can replace the open integration over dl as closed integration. So it is closed line integral e bar dot dl is equal to 0. Now what do you mean by closed line integral e bar dot dl is equal to 0? This mathematical expression, I'm writing it in the text, as a sentence. So what I'm saying, that the circulation of the electric field or electric field intensity along any closed path, take any closed path, is equal to 0. So if you have any electric field, so if you have, this is my open surface, okay, so you have an electric field, and this electric field is something like this, and this is maybe created by some source somewhere here. I don't worry, but this is my electric field here. Now if you have this already disturbance here, and if you move from point A to point B, if I move from point A to point B, then I do some work, as we have already seen. I will do from work to move from point A to point B. And then what it is saying, that if you return back from point B to point A using some other path, so this is path 1, this is path 2, then you are doing a closed line integration. You are doing a closed circulation. And if you do this closed line integration in any electrostatic field, if you do this closed line integration, you will see that you will get a 0 answer. You will get a 0 answer. And this is what this expression is saying. And those fields which satisfy this condition, that a closed line integral in the presence of that vector field is equal to 0, then those vector fields are called as conservative. That means your VAB is independent of the path. See, so first it is independent of the path, whether you go in from path 1, from path 2, from path 3, independent of the path, and this is becoming 0, and therefore it is becoming conservative. So these are the two very, very important properties of your electrostatic field. That is, the electrostatic field is conservative because the potential, if you go from point A to point B, will become independent of the path. Conservative. This field is conservative. So if you go in one direction, when it loses in the other direction, you may gain. So overall, it becomes 0. This is called as a conservative field. An example of non-conservative field, you can think it as a friction. Friction. So friction, if you move it in one direction, and if you return it back to the same initial point, in friction, you will always lose. You cannot gain. Whether you move it in one direction and return it back, you will always lose. So friction is a non-conservative field. But in our case, electrostatic is a conservative field. Okay. So I think it's time. We will stop here. And in the next class, we will take some relationships between electric field and potential, and we will do some exercise. Okay, so today we looked at what is the potential and what is the potential difference and its relation with electric field. Okay, so before stopping, any questions?